All right, welcome to today's Corundum developer meeting. Thanks to everybody for tuning in. The main thing I have for today are just some status updates based on stuff that I've been working on over the past couple of weeks. But I will say that, standing invitation if anybody wants to present at one of these things, some work you've been doing that's of interest to Corundum, let me know, and I'm more than happy to turn it over to you for a few minutes. So let's go ahead and get this ball on the road. So get this ball rolling. Right. So status updates. Previously, I've been doing a bunch of work on the batch completion write support, which is starting to look pretty good. But as happens occasionally when you start to make optimizations and adjustments to improve the performance, sometimes you start running into bugs that previously were, hidden. So yeah, as you start to crank up the performance, you hit some edge cases, some corner cases that you might not have hit in testing previously. So I've run into two rather major bugs so far. The first one, I suspect I may have cropped its head up in some of the testing previously due to the exploration that I've done of what was going on there. But that's now fixed. And then another bug that cropped up in some of my testing was a bug in relation to what the PCI Express IP core is doing. I thought I had a workaround for that. My workaround didn't work, so I need to take a different approach. I'll talk about that more in a minute. And then the other main thing I've been working on is batch completion write support. So once that's squared away, then I'm going to do the variable length descriptor support, and that's going to provide a pretty significant, I think, performance improvement to the Corundum core logic, just in terms of moving data to and from the host. All right, so just a brief overview of what's going on with these bugs here. So the first bug was a transmit engine problem, and basically there was some bad prioritization where merging early and late request status responses resulted in some of the early response getting lost. So the reason there's two different ones is when a queue operation fails, it doesn't go through the whole process of reading the descriptor and sending the packet. So we want to get that response back to the scheduler as quickly as possible, such that it can reschedule, or I guess in this case deschedule, that queue, and start sending us more good, hopefully, transmit requests. So that prioritization was screwed up, and as a result of these responses getting lost, slots in the scheduler were getting stuck, just waiting for a response, so it never gets freed up. And this effectively reduces performance because the scheduler can only generate one outstanding transmit request per entry in its little internal table. So if we have some of those table entries stuck, then it can't issue as many operations and the performance is reduced. So I made a change in the transmit engine to fix that. I posted about that on the Zulip. So that's now fixed, and pretty simple change to apply, or you can just pull down the latest code if you can do that. And then I ran into a bug on the PCI Express hard IP core on the UltraScale Plus devices. Basically, under heavy load, it seems like there are some operations that are disappearing. I'm not sure if it's the requests that are disappearing, or the responses, or the core somehow filtering out the requests. Not exactly sure what's going on, but it's not doing what it's supposed to do. It seems like this bug is related to the completion buffer management logic inside the core. So on the Xilinx devices, there's a, I believe it's a 32 kilobyte buffer that is reserved for completions for requests that are sent out over the link. And it won't send out a request, or at least it shouldn't send out a request until it has reserved space in this buffer for the corresponding completions. What I think is going on with this bug is that logic is getting screwed up. It accepts a completion it's not supposed to accept, and then it like overwrites some of its internal logic for tracking completions, and then everything gets screwed up. And I'm presuming what happens is when those completions actually come back for that operation that got kicked out, then they get dropped. basically. The interesting thing is they don't seem to be getting dropped before they get sent. So I think they actually get sent to the host because the core reports a sequence number associated with every operation that you start. Well, it's more like you give it a sequence number when you give it the operation, and then when it sends it, it gives you the sequence number back. And it uses to keep track of how many transmit or how many read requests and write requests are in the pipeline at any given time. And for the requests that are getting screwed up, you do see all the transmit sequence numbers. So anyway, I posted some more details about the debugging process and the Zulip if you want to go take a look at that. I thought reducing the number of tags would solve the problem, but apparently not. So even after dropping the number of tags, I'm still seeing hangs associated with this bug. So yeah, I think what I might need to do is to implement the tag management in terms of using the hard IP core to do that, because basically the Xilinx PCI Express IP core, it allows you to do the tag management in two different ways. I mean, ostensibly allows you to do it two different ways. It seems like one of those ways doesn't quite work correctly. Either you can manage the tags yourself and make sure that you never send the same tag to the hard IP core until you have no more outstanding requests for that tag, or the core is also capable of keeping track of how many outstanding requests there are per tag, because it has to keep track of this completion buffer. So what you can do is have the core instead assign tags. This does require a bit of reworking in the DMA engine in order to support this, especially if you want to be able to support both, because the Intel devices don't do this, so you have to do the tag management yourself. So in order to implement this, so I'm assuming that if we let the core do the tag management, maybe we won't run into this particular bug. We'll see. Not 100% sure about that. I do have a post on the Xilinx forum that Tracy Burnhat reminded me of, so I went ahead and updated that. But yeah, so not sure exactly what's going on with the core. I'm hoping that if I switch over to using the internal tag management, that will solve this problem. So what I need to do for that is to implement the tag management in the hard IP core model that I have in CocoaTBX PCIe. Then I need to update the DMA engine to use that, and then obviously integrate that into Corundum. So a few steps down that need to be taken for this to work. And I'm currently working on CocoaTBX PCIe to implement this functionality along with a couple of other small modifications. So anyway, that's what things are looking like right now. Two relatively serious bugs. One of them pretty easy to fix. Second one looks like it's going to be more complicated. Also, not 100% sure it's going to fix the problem, but fingers crossed. I guess this is kind of similar to the previous bug that I had with the hard IP core, where I was getting corrupt TLPs on the RC interface. That was solved by switching to the segment interface. Again, as you start bumping up the performance, you start running into these issues. So anyway, at least I have a reliable way of testing this and triggering it. So we'll see. I guess that does mean that when I fix it, it might not actually be fixed. I might need to find some other way of trying to trigger it, but we'll cross that bridge a little bit later. All right. And then we get to the batch completion rate support that I've been working on for too long now. Anyway, the idea behind this is to batch the completions that are getting sent back to the host, and instead of writing every single one of them separately, write them in blocks. And then at the same time, we can do we can batch generation of or not so much batch, but delay the generation of interrupts and events, and also do the queue pointer write back kind of all at the same time. And this performs basically some level of interrupt coalescing. So I have an initial version working in hardware. The performance is similar to kind of the stock version that doesn't have this. The hope is this plus the improved descriptor fetch that's going to be set up for the variable length descriptor support will provide a significant performance benefit. But you know, we'll see once everything's working exactly what that looks like. So let's take a look at a couple of numbers here. I've shown these graphs before, but I keep adding new ones at the end as I do stuff. So this is kind of the baseline performance right now for a 9K MTU. We can hit 100 gig with, you know, about 6 hyper processes running. If you run them separately, if you run them at the same time, it tops out at around, you know, 70 gigabits per second or so. Not sure exactly what the bottleneck is here, but that'll be something I need to track down. Now, if I turn on write back, so this is kind of the initial version of write back that I implemented. This one here is just writing back the Q pointers, but the driver is not actually looking at those, it's still reading the Q pointers over MMIO. It does have a small impact on performance. So yeah, like the RX performance it has this little dip in it, and that kind of moves from about 12 processes to about 6. So that's not particularly great, but this one is writing that back for every packet that's sent, which is not ideal. And then if we turn on the full Q pointer write back, so the driver is actually using the written back pointers, then the performance is, you know, significantly degraded. The other thing that's interesting is that the TX performance when you run both the TX and RX at the same time just takes off. So that's kind of interesting. Let's see. And then I also went ahead and implemented IRQ rate limiting, just a very simple technique of whenever you fire off an interrupt, you then kind of pause that IRQ channel for a few microseconds and coalesce and delay any interrupts on that particular channel that might be triggered. Adding that, it helps quite a bit with the RX performance, but it's still not back to where it was. So, but it does show that delaying the interrupts does improve the performance here. So, presumably, what we're seeing is in large part due to limitations on the software side. Right. And now this is the first graph that I have with the new full completion write back support. You might notice this ends at 12 instead of 16. That's because of the PCI Express bug. But the performance is looking, you know, comparable to the to kind of the current baseline. So you'll notice both of these will fly up all the way to 100 gigabits per second, right around, you know, 5 or 6 hyper processes and stick there. So that's what you want to see. It's also interesting to note that the TX performance seems to kind of dominate over RX when you're running the two at the same time. So not sure why that is at the moment. Well, I'll definitely have to take a look at that, but at least we've kind of clawed back some of, you know, this kind of stuff. So that's good. I also ran this at 1500. This is the baseline. This one was taken more recently, so this one actually includes IRQ rate limiting, but not any of the other stuff. Yeah, no write back and MMIO pointers. So those are all the Q pointers are accessed via MMIO. So this tops out at around, you know, 80, 85 gigabits per second, something like that, and then groups a little bit. In the TX direction, and RX is down here. I think this is mainly a software limitation, you know, memory management related in the receive direction. So that's a 1500 with the old setup. With the new completion write back support, everything looks about the same, but we definitely see a significant boost in the TX direction. So this goes from what, around 80 or so to, you know, maybe around 90 gigabits per second, maybe a little bit less than 90. But the big thing is this this tail here looks a lot better. So yeah, we'll have to see how that looks once we get everything operational. But this is definitely a promising result at this point. And this one actually goes all the way out to 16 because for whatever reason that PCIe bug is only cropping its head up for 9K MTU. So not entirely sure why. Anyway, so that's the batch completion write support. I haven't really changed the implementation very much. I've just been hunting down bugs primarily. So yeah, it uses about 64K of buffer space, which is basically the smallest buffer that you can build out of block RAM when you have a 1024-bit wide data path. So it doesn't make sense to make it smaller than that. So this is 64 rings at 1024 bytes. And that corresponds to 32 entries. And then that is split across TX, RX, and event rings. And, I presented a couple of details about how this works in terms of it uses kind of an internal scratch buffer, and then that gets aligned with the buffer and host memory because we're just truncating the pointers. So they all wrap at the same point. And then this does a block write and Q pointer write back that are triggered when you cross these internal boundaries, and then also by event generation. And the event can be triggered by packet count and or timeout. And maybe other stuff would be if somebody has any other ideas for potential triggers for write back and whatnot, we can certainly look into implementing that. And then once this is done, then I'm going to work on the variable length descriptor support. And fortunately, I think there's a fair amount of code that I'm going to be able to reuse from the completion write code that can be utilized for variable length descriptor support. Well, I guess one of the things that I didn't put on the slides here, I've been talking with a couple of folks about implementing some slightly different protocols. So up until now, I've mainly just been talking about sending and receiving just pure Ethernet packets with Corundum. But if you wanted to do something like, for instance, a TCP offload engine, where you might want to have one queue per connection and then only transferring payload data instead of a bunch of packets, how that might work kind of at a system level. So one of the things I'm starting to think about is, okay, if you wanted to do something like that, is there additional queue state that you might want to save? So one of the things that I was thinking about previously is having an LSO offset that you can use for if you want to send, if you want to have one descriptor correspond to multiple packets, right? Your network stack might hand off a 64 kilobyte descriptor, and then you want to have the hardware slice and dice that up into a bunch of packets. And actually, if you aren't using TCP offloading and you're using something like just segmentation offloading, then there will be a header plus that gigantic 64 kilobyte buffer, and then you have to modify and duplicate the header across all the packets. For like TCP offloading, you would be generating the header and then attaching that to the contents of the buffer. So in that sense, it's similar. But if you're going to implement something like TCP offloading, you also need to have kind of a window size that you can go back and potentially replay previous packets. And this would also be necessary for RDMA, because RDMA does have an acknowledgement protocol, and you can replay stuff. So what I've started to think about is, okay, maybe we need to have the potential for some sort of window management built into the queue management logic that can be utilized by protocols like RDMA, or if you're going to do some sort of TCP offloading or NDP offloading or whatever, where you want to do one queue per connection, then manage retransmissions over some window size. You might want to do something like that. So I haven't figured out all the details yet, but I'm starting to think about that. If anybody has any ideas, let's we can discuss that. Right. Let's see. I think that about rounds it up for stuff that's actually seen some progress in the past 2 weeks. I still have some slides on the various details about the variable length descriptor support, but I presented that before and nothing here has changed. The queue state storage, that has been, well, I mean, this is still current, but I've been working on the queue state storage for the completion write back support, and it seems to be working pretty well. I did have a couple of bugs in there I had to work out, but seems to be doing what it's supposed to do at this point. Let's see. Yeah, so that about rounds it out for that. Was there another change that I made? Oh, I did drop, let's see, I dropped the ARM continuous bit. I'm not sure if I announced that before. I dropped that because when I was looking at the completion write support and the event generation, it was unclear the best way of handling the ARM continuous bit without jumping through a bunch of additional hoops. So I just said, okay, we're going to remove it for now because I don't think anybody's using it anyway. And we can circle back around to that later on, perhaps once we can get the semantics figured out a little bit better. It looks like to implement it properly, some additional queue state might be necessary. What that looks like, I'm not sure. Let's see. I think that's about it in terms of the queue state stuff. Yeah. Okay. Let's see. And then I have, carry over to do items management softcore that I'll do that at some point. 10G, 25G switching. We have this, most of the hardware for this here. Once we have the softcore, then we can actually get this connected up to the driver. Clock info register block, another thing that I need to get squared away at some point. And that brings us to the to-do list for the stable release. So the variable descriptive support, completion write back support, that's what I'm working on now. So hopefully once I get that done, then there's only a couple other little, well, maybe not little, but a couple of other things to do before I might be able to start cutting, version releases. So that's how things are looking at this point. Does anyone have any questions or comments at this point? All right. So no questions or comments on the status. So at this point, just if anyone has any general questions or comments, fire away.
Can you explain batched completion in more detail if it's possible?
Yeah, sure. The high level for the batch completion rights is that we're trying to accomplish a couple of things. The first one is we're trying to make better use of the PCIe link. So each completion right now is 32 bytes in size, and you got to write one of those out for every packet. Well, I guess right now it's every packet, but I guess eventually if you do something like LSO, it's going to be one descriptor can optionally generate one completion. So the idea with batch completion write is instead of writing every completion out separately, what we're going to try to do is spool them in some sort of internal storage and write them out in blocks. So this is going to reduce the PCI Express bandwidth usage, because if you're writing out a bigger block, then you have fewer TLP headers that get sent, right? 256 byte block is going to have, one header versus, let's see, I guess if you're going to write those out separately, that would be 8 blocks of 32 bytes. So you're saving 7 TLP headers potentially in a lot of configurations. But the flip side, it adds some complexity in terms of, managing these internal buffers and, managing all of these write back operations. The other aspect to this is if you're going to be doing all of that management, then you can also delay the generation of events and delay the write back of the queue pointer information based on, the number of completions and potentially some timeouts and potentially other things, which also could improve utilization and overall performance. So like the queue pointer write backs, that's a big one, because those, I had a comment on that a while ago about you might as well pad out the pointer write backs all the way out to a cache line size, because there can be write combining hardware that you don't want to be, overloading. So if you just write out a whole cache line size, and that ends up being more efficient. So for the queue pointer write backs, those are all padded out to 64 bytes. So if we're doing a queue pointer write back for every packet, that's a lot of PCIe traffic, because the queue pointer itself is only 16 bits. So with the batch completion write support, we can also defer doing the write back of the queue pointer until we've seen a few packets. So now you're not writing this out for every packet, you're writing it out for every 8 packets or 10 packets or whatever. So That's kind of the idea. And the same thing, you can also defer the generation of the event. It doesn't make sense to generate an event and generate an interrupt after receiving one packet. It might make sense to do that after you receive 5 or 10 or something like that. Obviously, this is a trade-off versus latency. But if you're trying to hit, full line rate, a couple of microseconds of delay is not really a big deal if it means that software can do its job more efficiently. So that's kind of the idea.
If for some amount of time, if no packet arrives, do you think we should have timer and send completion with less packets? I mean, about less packets.
Yeah, there's a timeout. It's you can
Oh.
configure the number of packets and the timeout time. So I think the default timeout time that I'm using right now is 10 microseconds. But you could set that to 0 if you wanted, and then it would just fire off immediately after each packet.
So whichever finishes first will be applied, right?
Yeah. If you hit the packet count, then it fires. If you hit the timeout, then it fires. Yeah, it's. I guess you could set it up so you got to see both, but yeah, right now it's just either or.
Thank you.
Yeah, sure, no problem. All right. Does anybody else have any questions or comments? I know the folks at MLE usually have some questions, but I guess they're holding off if so they're not monopolizing time. But if nobody else has any questions or comments, then Joachim and Ulrich, go ahead and ask away if you have any questions. Nothing. So everything's working great over at MLE. I guess so.
Double unmute. Now I'm here. Yeah, no, I guess we are working through our testing now for the product release and doing a lot of performance testing. We are running it at a much lower rate at 10G, but also smaller ETIE bandwidths. So I guess we might be experiencing similar effects that you will see for the higher bandwidth tests with TX eating up bandwidth for RX. And at least there is some impact and difference when you run traffic unidirectional or bidirectional at the same time with a device. Or through a single interface, actually. That's the current test case. Yeah, right. But yeah, we've been just working us through that, and yeah.
Okay. Yeah, I guess so there are a couple of settings that you guys can potentially try adjusting that might have an impact on the throughput. There's a bunch of basically table size parameters in the config.tcl script, and most of those you can just bump up and it'll maybe consume a few more resources, but it could potentially help improve the throughput.
Yeah,
I'm not sure if you guys have looked at that. But most of those you should be able to just play with, and maybe it'll help, maybe not. I know one change that I made concurrent with working on these on the updated descriptor write support is to bump up the transmit and receive operation table size from 32 to 64. I know that there's also tables for the queue operation size and the descriptor and completion, the descriptor fetch and completion write modules. Although it's possible some of these have not been pulled out to parameters and they should be, but anyway, all of those you could take a look at and see if they impact the performance at all. Because for small packets, they could have a pretty significant effect.
Right. Yeah, that's one aspect we're definitely looking at. Yeah, varying these top level parameters and yeah, see whether they help.
However, I think the central point is we were kind of leaning towards the ZCU 106 design for our own hardware. And we have to check that, but we are really similar to that in terms of parameters, in terms of MQNIC core parameters, I would say. So I'm currently a little bit skeptical if that really helps to change something from the point of view of the ZCU board, which yeah, delivers the performance with an kind of equivalent design. So to perhaps to add to that, what Uli said, we also kind of yeah, looking into wondering if there's any difference regarding Intel versus Xilinx. I think that has also to be mentioned.
Have you noticed a difference between those different devices? Or you're just wondering?
Yeah. So what we are currently testing is we are having we are basically building two designs in parallel always. And as a reference, we use the ZCU 106. Just so if something come up or we want to upstream something, that we have a reference that we both use. And in addition, we obviously build for our target device the custom card, and yeah, that behaves different. And right now, as Joachim said, we need to double check, but we think we are using the same parameter set for MQNIC core, but performance results differ for both.
Is it a pretty
we are
significant
running the
difference,
PCI.
or?
Yeah, I would say so.
Interesting. Well, so the main difference between the FPGAs is the PCI Express IP core.
Right.
So it's possible that so basically I know the Xilinx core is doing a number of things under the hood in terms of managing the completions coming back, and it's possible that will have some impact on performance, and you know it'll limit to some extent the number of requests that you can perform. So this is kind of what I mentioned before, right? It has this 32 kilobyte completion buffer with 256 tags. That doesn't give you very much per tag in terms of outstanding reads. So, but I guess there's also the question of, you know, how quickly the host machine turns the reads around. So yeah, that's the main difference that I'm aware of. So if you're running into limitations of what the PCI Express IP core is doing, then you know that's going to be limiting the design.
Yeah, and I guess at that point there comes a strange thing, which is UDP performance is different from TCP performance. I mean, UDP meaning fire and forget, and
right,
just making it through the stack and through the whole machine, versus TCP, which yeah, ends up getting much less performance in connection with retries, of course. Yeah, that adds to the current complexity we are looking at. Not only do kind of boards differ, which we think have pretty much the same MQNIC core, but on top of that, there seems to be a difference in TCP versus UDP.
Yeah, TCP versus UDP, that's definitely going to be more on the software side in terms of what's going on there. What you can do about that is a different story. I don't know. It's I think the issue may boil down to just on the TCP side, there's more kind of offloading options that are available. So like there's a lot of NICs that support the TSO, which is TCP segmentation offloading. And there's kind of a software version of that that is basically what Corundum is taking advantage of right now, which the idea is you basically do TSO, where you assume the NIC supports TSO all the way up until you get to the handoff to the device driver. And then if the NIC does support TSO, you just give it the TSO packets. If it doesn't support TSO, then you generate the headers for all the packets basically and hand them off at that point. With UDP, I don't think there's a good option for segmentation because UDP you don't have segments basically, you just have packets. So all the packets are processed individually, and that could explain most of the performance difference right there. I think there is some sort of offload for that somebody pointed me to a while ago. There might be some sort of fragmentation offload support, but you probably don't want to be dealing with fragmented packets. I don't think that's going to help. I think for certain connections, it might have been like Quick. They've run into the same problem at Google. So there is some sort of UDP segmentation offloading, but I don't know how generally applicable it is. And I'm not sure what version of Linux it was added in. It might have been called, I can't remember if it was UFO or USO. Let me see if I can figure that out real quick. But this was something that I looked at not too long ago.
I mean, we are aware of all these features which standard NICs have. On the other hand, we are at least trying to generate traffic which is rather usual. I mean, we are using 1500 MTU here, basically, or a little bit less even.
Well, I guess another question is, have you tried like the same UDP traffic generation with a normal NIC, like a Mellanox NIC or Intel NIC or whatever? And are you seeing a similar difference in UDP versus TCP performance?
We did try, yes. We established a baseline, and with the standard NIC, it's in this case these X710 Intel NICs. There's no such difference in UDP versus TCP.
Interesting. Okay.
I mean, to establish a baseline, we said baseline is as is, meaning, of course, this Intel NIC has all the features enabled, which are enabled by default, meaning any kind of offload, which might be there. But using standard settings, there's no difference. No difference means here we can generate 10 gigabits or equivalent minus overhead, and put that through a bridge. This is basically our setup: generation, bridging, and then a sync. And no matter what, UDP or TCP, we reach the 10 gigabit here from source to sync. No problem.
But you can't hit 10 gig with Corundum, it sounds like, at the moment.
Yeah, we can hit 10 gig with UDP. There seems to be no problem with UDP, but it gets really crazy with TCP.
Okay. So it's TCP. Okay.
Yeah, that's
what
what
I guess I misunderstood what you were saying before. I thought for some reason, TCP was
No,
working
no.
better than UDP. Okay,
No,
that's the other way
no,
around.
TCP
Okay, I
has,
see.
has way less performance. I mean, it's also very jittery. I mean, from run to run, you don't hit the same numbers. You hit the same range. I would say something around 2.8 to 3 point something, sometimes 4 point something. And looking at, we are doing iPerf here as you do, and we are reporting kind of every 3 seconds, and even within the same iPerf run, there are huge differences from 3 seconds to the next 3 seconds. Also in terms of retries, for example, kind of all over the place, sometimes 0 retries and then in the thousands. The window is going up and down like crazy. I mean, following the retries, obviously. And what we found so far basically is that we put in counters, packet counters after the MAC,
Yeah.
and compared these counters with what Linux thinks it receives, and the other way around, sending. And there we see that between the MAC and the host RAM, obviously packets are lost. Strangely, it's not the same number indicated by retries, for example. It's kind of what was it? Factor 1000. No, hold on. Factor 10. So
you're seeing more retries than packet drops? Or
yeah. At least when comparing these counters behind the MAC, receive side MAC, and then what ends up in host RAM, or what is recognized by the driver and then presented via ifconfig.
So one problem that I ran into when I started ramping stuff up towards 100 gig is that the host wasn't always responding to the PCIe TLPs to the read requests in a timely manner, and occasionally, when I think also wasn't necessarily releasing the flow control credits in a timely manner. Wasn't really sure exactly what was going on there, but it definitely helped to increase the RX FIFO size in the FPGA design. So what size are you running at right now? Is that did you just leave it all at 32K, or did you try bumping that up?
I don't know it by heart. I would say that it's the same thing as in the ZCU 106 design.
Right.
I'm currently looking at the diff of our config tickles.
Yeah.
And,
well, you might try bumping up the RX FIFO size and RX RAM size by a factor 2 and just see if that does anything.
Okay.
Because basically you should be able to read out of that out of the internal FIFO much faster than the Mac can write into it. So, you know, if the host has to, you know, it's not returning requests in a timely manner, then you can let a little bit build up and then it'll drain it out.
Okay.
Are you running at PCIe Gen 2 or Gen 3 right now? I know you were
yeah, that's another
Gen 2,
problem.
so
yeah, it's still another problem with getting timing right. We are still running at Gen 2, and had a problem there, which we think we fixed by doubling the width of the interface data path.
Right, yeah, you guys were asking about that.
Yeah,
Make it
right.
faster than 8 gig. I'm like, well, I'm not sure what's going on there. Then it hit me. I'm like, oh, 125 megahertz is less than 156. That's going to limit things. So yeah, with that doubled, then you should have like 16 gigs of bandwidth out of that, out of the RX FIFO at least, which should allow you to make up some ground against, you know, what the Mac is doing if there's some sort of a backup on the host.
Yeah, and in this scenario, we were then getting, at least when using UDP as a test scenario, we were then getting the 10 gigabit RX TX since we're doing bridging in this test case.
Gotcha.
So that kind of fixed UDP performance, to say it like this. But then we moved on to see what TCP does now, and yeah, it also improved. I mean, it went up, but not to the standard 9.4 something.
Right. Are you seeing a huge difference between TX and RX? Like TCP TX seems to work, but RX doesn't work as well. Is that
yeah, it's even more stranger now. I did a lot of tests in the last days, and the strange thing also is that when using just RX or just TX by yeah, doing the other part of the bridge using a standard NIC, then it's all good. So
interesting? Okay.
Currently we are at the point where we say, okay, something is happening when RX and TX is happening at the same time, and TCP is behind it. Because when doing UDP in both directions, it doesn't behave as bad as TCP.
That's quite interesting. Yeah, I'm trying to think if maybe there's a way that, reordering could be coming into play here, right? If somehow packets are getting reordered, that could be triggering more retransmissions. But I'm not sure where that would be taking place.
And that's what I thought in the direction of the adaptation towards the Intel PCIe core. If something is different there, which is not there in case of Xilinx, in case of the ZCU. I mean, what the thing which doesn't fit is that by a bidirectional UDP isn't that bad.
Right. Yeah. I mean, that's why I'm thinking maybe it's a reordering thing, because TCP could potentially be more sensitive to that. But I'm not sure where that would be taking place, because I've definitely tried to be very careful to preserve the ordering wherever that could potentially be a problem. So yeah, not sure what's going on in that case.
So one other fact I would like to mention is the concern that the queue size is simply too less, and the RX queue is simply underflowing, or the other way around, the completion queue overflowing. I think there's currently no register to check that, right? In the MQ.
To check what?
If the RX queue has gone into underflow once, or the completion queue has.
Oh, just kind of status information.
Yeah.
Okay, so the completion queue, if the completion queue overflows, you got a problem. But that's easy to prevent just by doing things correctly in the driver, right? You just got to make sure that you don't send more stuff on the RX. You don't post more stuff on the RX queue than you have completion space available. If you do that, then you never overflow the completion queue. But yeah, right now I don't have any reporting indicating that the queues are underflowing on RX. Well, I guess there's two things to look at. So on RX, you can either run out of descriptors, or you can have a bunch of stuff stack up in the completion queue, which is not going to overflow. But if it fills up, I mean, I guess that's kind of the same thing. If you're out of descriptors to put packets into, then obviously they're all sitting in the completion queue and need to be processed. But what you can do is run the mqnix dump tool while you're running iperf, and you can see all the counts.
Yeah, that's what we've done. Yeah.
completely consistent with each other when you do that, but it'll give you an idea of, oh, these are empty when they should have packets in them, or vice versa. If you see the transmit queues and you got 1,000 packets in each one, it'll be like, okay, that's a problem. If you look at the RX queues and you see that RX queues are empty, but the completion queues are full, that can give you an indication of where the bottleneck is.
Yeah, so that's basically what we've done. We even went into the driver and added a small if statement. So if the driver thinks it needs to refill more than certain amount, then print something, and the other way around for the completion queue. And what's interesting there is that's also something which I cannot explain currently, is that the RX queue, I mean, the biggest number which gets refilled is 64 descriptors. So, and we are currently using 512 entries per queue.
Right. So some
so-
of that could have to do with NAPI,
Right, the budget,
because
yes.
that gives you a budget. It's entirely possible I screwed something up there and it's not handling the budget correctly. My understanding is the way it's supposed to work is it gives you a budget. You're supposed to do work up until that budget, and then you're supposed to return back to NAPI, and then it's supposed to call you again if you didn't use up that budget. And that way
That's
you
also
can,
my understanding, yes.
yeah. It's possible I screwed something up there and did one of the checks wrong, or I'm returning the wrong thing. I don't know. That's possible.
Yeah.
Every time it calls, it should only do up to its budget, and then it should get called again during that same session before NAPI polling is disabled. So
Yeah,
I'm not sure how to debug that, but
I looked at this today, and I currently see nothing wrong.
yeah.
But the point is that it seems like the RxQ is not even near underflowing when the driver only needs to refill 64. I mean, I didn't put in any statistics or something, but the completion queue, every now and then it's let's say almost full. I use a threshold of 3/3 and something like that, and it's yeah, I would call it almost full.
Well, when the
every now and
queue is
then
almost full, then the queue that's feeding that should be almost empty. It might make sense to, when you print out one, also print out the other.
yeah,
And
okay.
then you're doing this in the driver, or you're doing this in the hardware?
Currently in the driver, just
In the
a
driver, yeah. So
minor
when you look
modification.
at the completion queue, you can also go look at the associated receive or transmit queue and take a look at how much data is in that queue.
Yeah, right. Okay. Yeah, that's a good point.
Because if you're only putting 64 at a time into the receive queue, then that indicates that the corresponding receive completion queue should never have more than 64 in it.
Yeah, and
if it is,
yeah,
then there's a problem. And I think the problem is in terms of how the driver is setting things up.
It seems like that, because almost full no, I'm missing the English math words. What if 3/4 is
3/4?
right? So if its fill level of the completion queue is over that, then I'm reporting, and this means given 512. This means that, as you said, something is odd. Something might be wrong there. And I first thought, yeah, well, that's the budget, the NAPI budget. But looking at the code again, it seems to be like this cannot happen, because I mean the loops are separate. The first loop handles the completion queue, and the second loop advances the clean tail pointer, which controls what the refill function does. But this second loop can only advance the clean tail pointer as far as the completion loop before that went, I would say.
Yeah, basically.
And
Yeah.
so the situation I'm seeing, yeah, it seems to be wrong. It doesn't fit the expectation. That's
Right.
also
So
one
whenever
thing
you
we
see
have to
weird
look
stuff
into.
like that, then it might make sense to go modify what you're printing and say, okay, let's also
Yeah.
look at the associated queue and just look at how much stuff is in there, because maybe
Yeah,
it has a lot less.
that's a
so
very
maybe it has
good
a lot more
point. Yeah.
space than 64.
Yeah, and that's why I ask: is there currently any status we can read out to kind of prove that there's never an underflow or an overflow happening?
Yeah, right
But,
now,
well,
no.
okay.
But that's one thing that I've been. So the statistics collection thing got added relatively recently in terms of the components for that. What I'm trying to do is go through and, add statistics outputs to various modules and then connect that up. So like the new completion write back support, it has a whole bunch of, strobe outputs, which will be connected to the statistics collection module eventually. But I don't have anything like that on the transmit engines and on the existing, queuing logic. So, or on the schedulers or on anything else really. So, mainly right now, the statistics collection, I think, just covers like DMA related stuff, which to start, but
yeah,
there's
sure.
certainly more stuff that needs to be filled in. So eventually I will be adding, more counters to that. And that might actually be potentially, well, I'm not gonna say it's easier than adding, explicit registers, but you could certainly, wire some stuff in there, and then just read out those counters, because counters are already there. And if you have that enabled anyway, and adding extra counters that way doesn't take up any additional logic resources, as it's all stored in a memory. So, yeah, I'm not sure what else to look at. Well, but
Yeah, I
definitely
guess-
just running the dump utility while the test is running can give you an indication of what's going on. Just because that just reads out all of the internal registers. So
yeah, so
you don't need to modify the driver to run that.
Oh well, it's an easy thing
Well, it's
to
also
do.
easy to modify the driver too.
Yeah, that's two very good points. Yeah. So on the one hand, you said the FIFO and RAM size RX related. I mean, this would be a quick shot. Just see if that, changes something. And on the other side, you kind of, encouraged me even more to look at the driver side, that there might be something wrong with the queue fill states, so to say.
Yeah.
Two very good points. Thanks.
Yeah, it's entirely possible there's other stuff wrong in the driver, because this is like the first driver I've written for Linux, so it's highly likely I've screwed something else up somewhere and haven't found it yet.
Yeah.
It works well enough with the testing that I've been doing that I haven't, raised too many red flags. I mean, I guess I the testing that I've done on the Zinc does indicate that there is a pretty significant difference between TX and RX performance, but I haven't done much detailed debugging on the Zinc yet. So I don't know if that, if there's anything to be delved into there. But
yeah,
I guess you would expect some differences between AXI and PCIe, in terms of, timing and whatnot. Oh yeah, so I guess I did do another test with the Zinc with the latest code, which does have that kind of first pass implementation of the interrupt rate limiting. I guess you guys can try, backporting that as well. It's just one additional module for that sort of man in the middles all the interrupt connections. And then you can there's an adjustable prescale value and adjustable timeout value. I think right now I have it the default value set to like 10 microseconds, but you can crank that up or down and see if it has much impact on performance. Reducing the interrupt rate, maybe helps things. I'm not sure how much difference it's going to make really, because ideally when you fire off the interrupt, then NAPI does its thing and it does some processing. And if you have a lot of packets coming in, then you shouldn't be firing any more interrupts. until things, slow down a bit and the interrupt is re-enabled.
Yeah, I mean, I guess we discussed this before. Pretty huge impact, or I don't know, some impact comes, or another way around, the page pool thing, the recycling of the buffers has an impact, and I'm not sure, how much to attribute to it. The Intel cards do both usually, but I guess I would guess 30% page recycling and 70% by coalescing. Or
okay,
that's would be my guess from tests we've done so far. So interrupt coalescing seems to be more beneficial than recycling the pages.
interesting. Okay, I mean, I think
no exact numbers here, but that's my gut feeling.
Right. Well, and I guess you potentially also get benefits from doing more complicated TCP offloading. So I know it's relatively common on Nix to combine TCP segments.
Yeah, of course.
In some
that's
way
another story. Yeah,
and
right.
That definitely helps. But that's much more complicated to implement. So
yeah.
Well, I guess you guys have a couple things to look into.
Yeah, definitely. Thanks a lot.
All right. Does anybody else have any more questions or comments, or?
Yeah, maybe we can just add some comments on the DPDK side.
Oh, okay.
So there were some more steps recently. I don't know when Joachim gave the last update on this one.
I think it's been a while.
Yeah, I guess so.
Yeah.
So right now we can do. So first we updated to, I think, DPDK 21 dot something. So it's a lot more recent.
This is a stable branch, or this is still also kind of an LTS branch?
Good question. I think it's LTS still.
Okay.
And we were able to, yeah, so we adapted to the new register layout anyway. That's already discussed. And we are now able to use multiple interfaces and multiple queues per interface.
Right.
Although, yeah, DPDK applications have to make use of multiple queues. So it's not buried inside the PMD, but an application may request multiple queues and then use it.
And if it doesn't, then it only uses one, right? Yeah, I mean.
Right, exactly. That's a kind of a default. And we did some testing with the forwarding app. So there's an app L2 forward, and there is the default test app. I think PMD test, which does almost the same thing. So it receives a packet
around basically.
Yeah, from one interface to another. So it always uses kind of two interfaces, and if you have four interfaces, then the third interface also loops out to the fourth interface.
I see. Okay.
And we use this.
Okay.
Right. And yeah, so we use this one, and we were able to run. So we used a packet generator on the outside to drive it, and yeah, we ran it at about 8 gigs. It's not. I think it could be more, but I think it's enough to make use of it.
This is on a 10 gig link, 100 gig link.
It's a 10 gig link, so it's the same setup we are kind of using. Actually, no, we have to check this. If we ran into the same limitation. It's a different board. Joachim, do you remember on which board we did the test? Did we run into the same limitation we had on with the other
Oh,
tests?
the data path width issue.
Right, which is kind of 8 gigabits. I think we have to recheck this.
Okay.
Yeah, no,
Anyway,
I think we were testing. Björn was testing with the ZCU one time, and the other with this Sidewinder
Fidus.
board,
Okay.
where we did our custom port to it.
Okay.
And so there should be no problem with the data, which I would say
Right.
in respect to PCI Express.
Right. Exactly. So that this is the other design, right? So yeah, so that's kind of the current rate. So there is actually, to be honest, no real optimizations done with respect to performance yet, but I think it's okay to use. Yeah, what we are currently trying to run is to get a more reasonable test case. Is we are trying to run DPD or iPerf DPDK, I guess is the name, which is a port of iPerf on top of, I think it's NAS, and which is ran on top of DPDK.
Right. You
and
need a
this
TCP
intermediate
stack,
layer.
obviously, for iPerf to work.
Exactly.
You went on mute.
Okay. Have I been interrupted right while I'm talking?
Yeah.
Yeah, somebody called me. Sorry.
Oh, okay. Okay.
So yeah, so the intermediate layer implements the TCP/IP stuff. That's obviously missing in DPDK. So that isn't running yet on our driver, but we were able to run it with an Intel card, so it's generally usable. And I guess once that's done, I think we call it okay.
So
because
you said it's not running yet, as in something fails, I guess. You've tried it, but something's not working.
yeah, I think there were some obvious callbacks missing, so there seemed to be quite some
I see.
optional callbacks that a driver can provide, and depending on the app has to provide. So
Okay.
these
And I
have
guess the
been
stack is
implemented.
expecting a bunch of those. So
Yes.
all right.
and now we need to have another look at it. So we first try to replicate it on an Intel device to make sure, is this working at all? Because it's yet another DPDK version. So there might be other items that miss. So it's actually an older version, because that has been an academic project and it has been abandoned at some legacy DPDK versions.
Which
so
one? iPerf or the stack? Or both?
Yeah, I think kind of both. This iPerf on top of DPDK. Well, the last time I had a look at which stacks are available and which applications. So these more generic implementations all were about, I stopped adoption like 2 years ago. I don't know. Seems as if somebody got its PhD and then that's it. So yeah,
Well,
we'll see. So,
that
but I think
occasionally.
Right, yeah, and that's fine. That's the academic world, right? You show it's working, and then somebody has to take over. Or
It's
yeah.
unfortunate when somebody makes a cool tool and then it just kind of disappears, fades into obscurity. But I guess if it's not interesting enough for, say, DPDK to take it over, then yeah.
Yeah,
Anyway.
right.
Yeah, so I
But
guess
anyway,
the question we wanted to answer is there some standard tool, some standard way of testing a driver for DPDK in a in a sense where one can say, yeah, obviously it works, like using iPerf on a NetF and Linux. That was,
I mean,
I guess, the
aside
question.
from using packet gen, I don't know. Although I guess what you could potentially do is with the kind of default forwarding app, you could just run iPerf over that, right, from a different host, and
Yeah,
see if
yeah,
that
sure.
works. I'm not
Yeah,
sure.
maybe if
that's-
so if we can make it work with some reasonable effort, maybe we just fall back to this and say, okay, DPDK is packet pumping, application targeting, and so let's do this and don't do, yeah, like
Yeah, it seems
network
that there's a couple of
application.
main cases for DPDK, right? It seems like it was almost originally built for forwarding and not so much for
Right.
applications. So that's why like the default app is just, hey, we're going to cross connect 2 ports because it's designed for, software-based packet switching and such. So they might not have kind of a bandwidth test application sort of thing besides their packet gen. You're expected to use maybe some external tool to generate traffic for a DPDK setup, because how would you test a packet switch, right? I think it's the same kind of thing.
Yep. Anyway, so that's the status on the DPDK side. So we're coming to a point where it makes sense to look at it, I guess.
Well, sounds like you got a few things working, so that's good, and you've actually have it updated now to work with the current version of Corundum, more or less. So
right.
Yeah, that's progress. Have you updated the repository you have for DPDK yet, or is that's a to-do item?
Yeah, that's a to-do item. So I guess
Gotcha.
we'll have another look at the iPerf thing. Although I think, maybe we have a discussion on Wednesday about this internally. If we just pull the publication up first and then later resume on the iPerf. Yeah, but let's see. I guess we need to do some cleanup again, as usual.
Well, that's how it works too. I mean, I always got to clean stuff up on my end before committing it.
Yeah.
The initial version
there's
never
another
looks all
thing.
that great.
Sometimes
cleanup isn't enough. Sometimes you got to be like, this sucks. Rewrite.
we need to do it differently. Now I know how. At least I think.
I mean
right.
That's like a common occurrence. The first, maybe even
first
revision, maybe even the first 2 or 3 revisions are like just figuring out how to do something.
Exactly.
Once you know how to do it, then you do it right.
and another thing happens. So once you push the version 1 out, people using it, then they know what they actually want to have. So the next thing will be different anyway. There is another thing. We just briefly talked about it, and it was about managing the Intel ODI interface. And we started doing this. We are currently implementing the iScan and generator checker procedures for this. So once this is working, I guess we will start a pull request on the XFCP side, because that's what we're currently using for this. So it's not integrated into the production design yet.
Gotcha. Okay.
But yeah, very interesting items. But we should discuss this different,
right, yeah,
in another setting.
Yeah, I guess. Fortunately, you don't need much logic to implement that, I think, other than just connecting the reconfig interface. So potentially it could be implemented in the production boards without too much difficulty.
Yes, it definitely is. The most work to be done is figuring out what the documentation wants to say.
I took a brief look at that, and they have like, what, 3 or 4 bits, I think, that set like the bit count, and they have some really weird collection of values for that. The
it's very interesting.
Much more regular. It's just 2 to the n, or whatever.
Very, very
Intel one is
interesting
some
register
strange
set.
combination of 2 to the n and 10 to the n. I'm like, really?
It,
Okay.
it sometimes it appears as if they are like, okay, we need 5 other bits. Where can we stuff them in? Here are 2 and there are 3. So that to get put together, it's 5 bits to configure something. It's like, really? There was not enough space to add another register? I don't know. It's
I
really
don't know why they do
interesting.
stuff that way. I mean, I guess it's one thing if they have some like legacy interface, but I mean, it's,
Yeah,
it's like the H
or if
tile,
it's-
right? So that's not used anywhere
it's-
else.
And it's not the first thing they built, right? So it's not the first FPGA with high-speed transceivers they ever built. It's I don't know, the 5th, 8th generation. So it's not like we don't know how to do it.
Right.
Really interesting.
Well, I mean,
Very
the other thing
interesting.
is like if you look at the Xilinx GTH and GTY and whatnot, a lot of the register assignments are exactly the same, and they've been maintaining them over multiple generations. So that
Mhm.
makes sense because, you know, then your software is, you know, it works across all the various generations. So maybe Intel has something similar going on. They don't release enough documentation to be able to tell for sure.
Well, maybe they actually cut some trails off from before StratX 10. That also might make sense if that now goes on and stretches across the H tile, E tile, P tile. I don't know, but we'll see. So
Yeah,
at some
I don't know.
point, I hope that, yeah, that this happens. Even for them, right? It's much more easy to copy paste the register set and add information to it rather than creating it from zero all over again.
Yeah,
And
that's true. Well, hey, look
always
at
like,
look at x86 assembly, right? That abomination. What is
hmm.
x86 in general? Who made that? Is this a mystery?
Okay.
That
No
No,
explains
comment
many
anymore.
things, you know?
it just grew like that. Nobody made that.
Yeah. Maybe it's the same here. I don't know. So, but anyway, I guess sometime around this week, I expect to have a setup that is running bit error rate tests.
Nice. Well, yeah, I guess there's two
So-
aspects to that, right? One of them is a bit error test. The other aspect is the iScan stuff.
Exactly. Which is a little bit more complicated, but yeah.
Yeah, I mean the bit error rate is you just set it up and run it, and maybe you read the error counters occasionally. With the iScan, you got to jump through a few more hoops. So, anyway,
Exactly.
yeah. Are you going to use the same, you know, CSV format as that I put together for the Xilinx ones? Then you can use the same plotting script.
Exactly. So the idea
Okay.
is to create a user interface that is as similar as possible. To enable reuse. But yeah, I guess we can further discuss this once it's somehow working, and then we provide the pull request, and we can have a discussion about if you like to have it differently or if we should adapt
Right,
it somehow. And then yeah, we get a more consistent view. Because I never
Definitely.
used your implementation on the designing side yet, so I guess nobody else did.
Right.
So it
Yeah.
definitely makes sense.
Well, yeah. The other thing I was trying to figure out when I wrote that is, okay, what if you want to do the iScan on multiple channels at the same time? There's no reason you can't run multiple of these in parallel if you write the code in a nice way. So I tried to do something where you don't need to use any weird multi-threading or something to run across multiple channels in parallel. And presumably, if you do the same thing on the Intel devices, then that'll also work.
So our
and I
target
guess-
is
I guess the
definitely
latest-
to run multiple parallel scans.
Right. Yeah, because if you have multiple interfaces, you might as well.
Exactly.
Yeah. So in the Corundum tools and the transceiver utility we have right now, it should be set up in a similar way for, you know, running iScan across multiple devices. I think I put more time into working on that on the Corundum side than on the XFCP side. But yeah, it's possible that some reworking needs to be done on the XFCP side for stuff to be usable. I think it might make sense to add another utility for that, perhaps, so you can run that separately. Not sure. I think there's
Yes.
some reorganizing that needs to be done. Perhaps I just haven't had time. It's like a lot of this stuff. It's all kind of, you know, needs based. If I need this capability, then I implement it. If I'm using it and something doesn't work, then I fix it.
Exactly. And yeah, it's a tool, right? So and
Yeah.
it advances with the use of it.
Yeah. So most of the time, there's no updates to XFCP at all. Is it abandoned? No, it isn't. I just haven't been using it. When I use it, then there's some commits.
Right.
That's kind of how things work.
Yeah. So I guess that there's another way of using it that might also, yeah, create a pull request. I'm not sure yet, because we are using, well, not in this use case, but in another use case, we are using XFCP on top of LabGrid, and LabGrid provides the actual communication with the serial port. So we can't open a device, but it's a indirect access method. So I guess we will open a pull request, adding another way of using a serial port.
Well, so how does that work? You're opening like a named pipe to LabGrid or something, or what? How does that interface work?
LabGrid
high level
is Python as well, so we're using a class of it.
Ah, I see. Okay. And then how does that work on the FPGA end?
Well, on the FPGA, there's no change. It's just the way the software side is handled. So the indirection is
okay. So LabGrid doesn't have any component on the FPGA. It's just like
no.
It just manages the serial port. Okay.
So the idea of LabGrid is you're having, like, I don't know, hundreds of boards, and you now want to run a test on some similar board for I don't know, board 100, and you don't know where it is. It may be on the other side of the planet, but you want to connect to the serial port. You just say, okay, hey, that LabGrid client, connect to this serial port and to this board, and use the serial port, and it just returns the corresponding object for doing this.
I
and
see. It
under the hood,
tunnels the serial traffic to the board, basically.
Exactly.
Okay.
And under the hood, it uses standard Linux utilities, so it doesn't re-implement this, but it uses the, I don't know, net console or something. So it's a standard tool, right?
NC Netcat? I don't know. Maybe not.
Not sure.
Whatever.
No, I don't.
Not a big deal. Yeah.
Right. But anyway, so under the hood, it always uses standards tools as long as it can, and it's just about distribution of information, and you don't need to remember which port you use for which board, for example. So we use it for JTAG as well. I don't know.
So does it also manage loading bit files and whatnot?
It can.
It can. Okay. Or I guess communication with Vivado or something.
Yeah. So one side is you need to have a hardware server running that is hooked up to the board, and you need to know where is it running and on which port is it providing its interface, right? So that's all hidden by the service. So you're just saying, load something onto this board, and the system knows where to communicate with.
Gotcha. Okay.
So that's the idea. You have a config file, and these, it's called place. For us, one board is one place, and you have multiple interfaces for this place, and you can connect to a place via this client.
LabGrid thing this is something that you guys built internally, right? Or this is some third-party thing?
No, that's third-party open source.
Okay, I see.
We do some extensions for it from time to time, which we also try to get back into the public. So it's definitely public. So usually what we do, if it's regularly used on our site, we add a pull request, and at some point it might get into upstream.
Gotcha. Okay.
Yeah, so that's just the way we organize our boards, our setups.
Yeah, it makes a lot of sense if you have a lot of boards. I guess
Yeah.
it can get complicated if you're managing a lot of interfaces off of those boards, right? I mean, it's one thing if it's just USB and JTAG, but if you're adding PCIe and Ethernet, and you need another host to communicate with for Ethernet, I can definitely see things getting complicated. Anyway.
Yeah. Anyway, right. That's a different discussion.
Yeah. All right.
But nothing else from my side, I guess.
Well, cool. Hopefully, you guys will have some interesting stuff to present about the iScan and whatnot soon. It'll be interesting to see how the Intel ODI stuff performs. I'm assuming it'll be similar, but
Yeah, at least from the point of view of using the Intel tools, it seems to be pretty similar.
all right. Nice. All right. So does anybody else have any questions or comments? Or I guess we're definitely well over time now, which is fine. Let's see. I guess we got Adam, John, and William. Either of you guys have anything you want to ask? Any questions or comments?
No, thank you.
Nope. All right. All right. Well, I guess we can go ahead and adjourn for today then. Oh, Joachim says LabGrid uses SEER2net. Okay. All right. Fair enough. All right. So I guess we'll go ahead and adjourn for today. Looks like 2 weeks from now will put us on what, October 10th. All right. At some point, we're going to have a time change due to just daylight savings in the US, clocks bouncing around. It would be nice.
Yeah, we are having it first, I guess.
Yeah, I'm not sure who's first. I think it's like November, maybe something like that. So
yeah, you're in 5th or 6th of November, and for us it's mid of or 20th of October. I think it's 1 or 2 weeks different.
Gotcha. All right, so next meeting will probably be at the standard time. Looks like that's on the 10th, and then one after that'll be on the 24th. So all right.
Yeah.
Fair enough. Always something to be aware of. Don't want to be off by an hour. That's embarrassing. All right, but it happens. Early by an hour, fair enough. Late by an hour, that's annoying. All right. Anyway,
thanks, Alex. So have a good day.
Yeah, sure. Same
Have
to
a
you.
good 2 weeks. Thank you.
All right. Talk to you.
Thanks.
Thanks a lot. Bye.
Thanks.
Bye.
Bye.
Talk to you.